Hey everybody, Dave Lindbergh in Hong Kong with another episode of the THD Podcast. Thanks for joining us today. Today we have Infineon joining us from Germany, a couple gentlemen joining us from there. But before we get into that too much, we want to mention our sponsor, the Audio and Loudspeaker Technology International. Especially during these COVID times, we encourage people to take whatever methods they can to network, whether it's LinkedIn or whatnot. A lot of people do that. But Alti is another good outlet for people that are developing audio products. So we encourage anybody that's watching to go take a look at the Alti site. We'll put the link up here so people can check it out. But without delay, today we've got a guest host with me today from the Philippines, Mr. Colin Ward. How are you doing today, Colin?
I'm doing good, Dave. How are you?
I'm good, thank you. Thanks for helping out today. Colin's an electrical engineer, everybody, and he's based in the Philippines. He knows a lot about audio, so he'll be helpful with this panel discussion. So joining us from Germany, Somu Goswami. Did I get that right?
It's Goswami, but close enough.
And he's a system architect from Infineon for MEMS devices, and also Julian Kornprobst. Is that correct?
Kornprobst, but yeah, it's a very Austrian name, so yeah.
I thought when I read it, I thought it was Prost, so I was thinking of cheers.
That's yeah. No, that was actually, I think on the very first day of at university in the first semester, someone came up with that. So, the Kornprobst.
So yeah, thanks guys for joining us today. And yeah, so in Infineon, they do a lot of semiconductor devices for different applications. And I think today we wanted to focus on the MEMS devices and find out as much as we can about them and what you guys are up to. It's a company, it's been around since 1999, so there's a pretty deep history. Originally part of Siemens, I believe. So
exactly.
And it's in fact one of the top 10 largest semiconductor companies in the world. So there's a lot to unpack, but let's just try to focus on the MEMS devices today. So maybe Somu and Julian, maybe just give a quick one at a time introduction of yourself, and then we'll jump into Infineon.
Perfect. That sounds great. So let me go first. So first of all, David and Colin, thank you so much for giving us this opportunity on your platform, on your THD podcast to participate. We have seen some of your videos and we found them to be extremely exciting, and it's a privilege to be on this platform and share our insights on how we see where the MEMS microphones, where the future of audio lies, and in which direction we are going. So I'm Somu. I'm part of the technical marketing team for MEMS microphones and MEMS sensors at Infineon Technologies. I'm a system architect, mostly focused on things that are happening outside the microphone, mostly focused on the application side of things. What are the use cases that are there now? How can we improve them? And what are the use cases that would come in the future, and how we could achieve them, how we could make the right products to achieve them. We work together with product marketing team, basically to drive this vision forward to bring best in class audio performance to all the consumer devices.
Okay, Julian?
Yeah, thanks, David. Also from my side, thanks to both of you, David and Colin, for giving us the chance to be here. The audio community is, yeah, I guess people know each other. So it's when we saw basically the guests on the THD podcast, we saw, yeah, this is part of the audio community, so it's great to be here. I'm Julian, also based in Munich, like Somu. I'm in the product marketing team for the MEMS microphones here at Infineon. And yeah, like Somu, I tried to look at also which applications MEMS microphones are used in and can be used in the future, and how these will develop. So Somu and I work closely together here from the business, marketing, and the technical and engineering side.
Okay. All right. So yeah, maybe without too much delay, maybe let's jump into a presentation and start walking people through the MEMS devices from Infineon and how they fit into the audio puzzle.
Sure. All right, then I'll start sharing. All right. Okay, you should be able to see my screen now.
Yeah, perfect.
All right, perfect. Yeah, so Infineon MEMS microphones. David, as you already said, we from Infineon, we are a global semiconductor company now. After the acquisition of Cypress Semiconductor, we are part of the top 10 with roughly 47,000 employees around the world. And I mean, we are playing a lot of markets, so automotives, power management, security, but also in sensor systems, which should be the focus of today's discussion. So yeah, at a glance, already said 4 main business segments: automotive, connected secure systems, industrial power control, and power and sensor systems. Power and sensor systems, PSS, is where Somu and I are based, or the division where we are from. And as you can see, we are truly a global company. So Somu and I are based in Munich, but also manufacturing, development, R&D, marketing is spread across the world. And as I said, within our division, power and sensor systems, where do we come from, so to say? And Infineon has a broad sensor portfolio. So if you look at MEMS sensors, we have air pressure sensors, time of flight image sensors, radar technology, CO2 sensing or environmental sensing, which was recently launched. And where Somu and I come from, what we call the smart ears. So MEMS microphones, and they're also covering all aspects. So from, let's say, cost optimized, lower performance to higher performance MEMS mics, which we will also get into later a bit. And yeah, the markets are booming. I mean, from smart speaker devices, smart home devices, hearables, conference system, and of course to smartphones. The MEMS microphones are found everywhere now, and that's good for us, of course, business-wise, and very exciting. And speaking of MEMS, yeah, sorry, Somu, go ahead. Yeah.
Yes, exactly. So as you know, with this whole boom, that basically exemplifies why the focus is at improving the technology and improving the audio ecosystem, be it having a machine level conversation, as in voice user interface devices with Alexa, Siri, and other voice assistant platforms, or be it a person to person, a human to human communication as well. So that's where the audio performance has to improve, and that starts from the device that basically picks up. That's where we focus on. So the microphone in itself.
Right.
Yeah.
Okay.
Speaking of, I mean, microphone itself, right? What are we talking about here? Yeah.
Exactly. So what we are talking about when it comes to microphones, there are 3 essential components: the MEMS, or the sensing element that would pick up your audio vibrations transmitted through change in air pressure. That's one of the focus. That's our MEMS, micro electromechanical systems. Then comes the ASIC, or the application specific integrated circuits, as you call it, that translates these vibrations into electrical signal, basically, be it depending on the MEMS, be it a single-ended analog output, or be it a differential output, or in digital domain, be it a PDM or any other form of digital signal. And the third, which is the most essential, is to bring these 2 things together. So a MEMS and an ASIC is integrated in a package with a sound port, and Infineon has shared its expertise across the market, not only in terms of expertise in MEMS or expertise in low power and low noise ASIC, but also in the package domain. And that's where we come from. So it's very important for any application, any use case, to understand these 3 blocks and how well you can optimize it for a given use case. Be it if you want to address a super high SNR application, basically you need to tune your MEMS, you need to tune your ASIC, and you need to know what's the right package that could bring in the best possible performance. And that's at Infineon, we try to work on all the 3 blocks and build up the expertise across all the 3 blocks, basically to bring the best possible solution to our customers.
Okay, great.
Yeah, and with that, I mean, I have to say it's been, we said we've been around for a while, and it's been a good ride, so to say. So according to market research, we are now leading in the MEMS microphone market based on die sales. And yeah, so what do I mean by die sales? So our business rests on, I would say, two columns. So on the one hand, what we call Infineon Inside microphones, where we sell MEMS and ASIC chips to packaging partners. You see a couple of them here, Gertec, Marion, GetUp, which are also found on our website. So really a broad portfolio. And then, as Somu said, right, important to control all the building blocks, MEMS, ASIC, and package. We are also packaging our own microphones. And here, as semiconductor company, the manufacturing also spread across our fabs across the world. So we have the MEMS design and manufacturing here in Europe and also in Asia, and ASIC likewise. So really focusing here on the aspects and try to cover all the business.
So that would be with like a Gore-Tech relationship. They would be taking the MEMS component or maybe the ASIC and then packaging themselves. So they take a sub-assembly. Okay.
That is correct. Yes. So on our website under this Infineon Inside, there are also from, for example, the Gertec portfolio some examples and also contacts. Exactly.
Okay. Very
and
good.
Yeah, with this we have been successful with these models, right? How to grow in the market, and yeah, it's important to have partners. I mean, also for the really high volume manufacturing. Okay. And yeah, looking at the history, and this was, I mean, I find this quite fascinating. If I ever ask around in my circle about microphones, they're always shocked to find how small the microphones really are. But I mean, if you look at a smartphone, cannot be too big, right? Because people, if they think of microphones, it's like the one you're using here, David, right? I mean, the capsule is a bit smaller, but usually we imagine bigger things. And that's, I mean, if you look at professional recording microphones, these typically use electric condenser microphone technology, which also have been this first miniaturized microphone. So I have this acoustics book. I think it's written in 2010 or so. And if you look there at making microphones small, it's talking about these electric condenser capsules. So those were the first ones back in 2008 when smartphones came along. Mm-hmm. The problem here, and Somu, you might want to comment on this as MEMS expert, is this ECM technology has some disadvantages in comparison to MEMS technology.
Exactly. So the ECMs have been the pioneers when it came to consumer devices at the beginning phase. However, there are the advantage. I would like to focus more on the advantages of MEMS technology is that you could do a large scale mass production of these MEMS and still hold on to a very low part to part variations. You could get excellent phase matching and excellent linearity performances. In addition to that, the other advantage of using the MEMS with the ASICs is that you can actually compensate for this tolerances by calibrating them. So you could calibrate each microphone at a production level. You could run an automated calibration setups where you could calibrate to fit it quite well. And as we see more and more devices using more than one microphone, it becomes essentially important to have matching sensitivity, to have matching phase and group delay responses. Mm-hmm. And that's the sort of a trend or the transformation that happened in the market, where a lot of the realization happened in this consumer space to move from ECMs to MEMS as the micro technologies, also microprocess technologies, also advanced over the course of the last decade.
So is there kind of a limit to how small they can go, or how small are they now? I mean, if I want to get 3 microphones into a TWS earbud, how do I do that?
Yes. So right now there is something called as some standard packages that you can opt for. The smallest one that's currently used in the market, which is super popular, it's also called as bottom mini. So bottom stands for the bottom port, and mini is the smallest footprint. That's of the dimensions of 2.75 millimeters times 1.85 millimeters times 0.9 millimeters in height. Yeah, but we are continuously trying to push the boundaries, because as you know, it's also the physical aspect of things. So the physics or the back volume that basically defines the performance to a certain extent, the SNR that you can achieve, and that's where we think that you could go further down, but at the cost of lower performance.
Yeah.
Yes.
Yeah, that was kind of what I was interested in. Okay, interesting. Thank you.
Exactly.
Yeah, and so that's, I mean, this trade-off size performance, right? This is also,
Yes.
if you look at, I mean, 69 dB SNR was in 2018, what we came out with from Infineon. But if you look, I mean, yeah, getting the highest performance while shrinking the size is still the challenge, right? I mean, and we know this from I mean, intuitively, if we look at, I don't know, batteries, for example, right? The bigger the battery, the more capacity it has. I mean, it's not a perfect one-on-one analogy, but yeah, you could have your earbuds for running for 48 hours, but then they don't fit in your ear anymore, right? So that's and that's where, I mean, we used to say that, I mean, there's a reason. If you look in the market, some consumer devices use ECMs, right? I mean, it's because they still need very high performance, and this is where we are also looking towards improving the MEMS microphone performance.
Okay.
And I mean, if I speak about performance, and yeah, it always depends, of course, on the application, what is more important. But if you look at performance parameters, I mean, any data sheet, you have different parameters to look at, which become more important or less important depending on your application, of course.
Exactly. So that's basically, I think some of it we already alluded in the last slide. So just to make a quick rundown on them would be, so if you start from the top left, it's high signal to noise ratio. It's a given that if you don't want to hear the hiss sound in the background continuously while recording, and still want to have a very natural conversation with the other person as if you're in the same room sitting together, it's a no-brainer that you need to improve the SNR or use microphones or array of microphones that gives the system SNR that's super high. We have seen cases, for example, for voice commands. So you would see some of the results as well that we have, where it is seen there are evidence that there is a potential benefit for voice command recognition improvement if you opt for a higher SNR microphones.
Absolutely, yeah. The far field detection really you need a good SNR.
Yes.
And that's the, particularly if you're trying to detect it in very high background levels.
Yes.
Exactly.
Yes. Exactly.
I've dealt with several customers who don't understand why they can't speak to a smart speaker 10 meters away from it when it's playing 100 watts of audio power out of it.
Yes. Funnily enough, we had very similar discussions as well with a lot of our customers to explain this phenomenon, and that brought us to actually just testing them and showing them the results. I think at the end of the day, it's the objective numbers is what helps in getting them on board, that this actually makes a big difference. No, totally agreed. Yeah. Yes. So besides SNR, which we know definitely is a key component, there are other components, be it in a smartphone form factor. You need a microphone that can not only capture the whispers, but also able to record it without any distortion at high sound pressure levels. So basically, you need the lowest of the low to be picked up really well, and the highest of the high to be picked up really well. So in short, you need a wider dynamic range, basically, to cover these aspects, where Infineon is focusing on different ways to enable this, to enable an ultra wide dynamic range, to basically make sure that no matter what happens, what situation you're in, the microphone shouldn't be the component that basically distorting any sort of an audio capturing. Yeah, and besides that, I think on the right side, you could see there are other key components based on application applications where they go into. So most of them are battery powered devices, be it a smartphone or a hearable device, and their low power consumption is again one of the no-brainers. So everyone would like to have a microphone which has super high performance, super low current consumption, and also cheapest, but
And small.
yes, yeah. And besides that, these consumer devices are also put into very wide, diverse environments now. So you would also hear about stories, people trying to blow an air gun into the sound port just to clean their smartphone because they saw it's a bit dirty. And that these kind of things play also a big role. So against water and dust production, you see devices which are coming out in the market with IPX4 and IPX8 or IP68, water and dust robustness, and those are the areas also where we think these are key parameters for the selection of the microphone or how we could enable this. So different aspects where we at Infineon like to focus on.
Right.
Okay.
Yeah, but I think from our research, and Colin, you jumped on it right away. I think what we focus on mainly is the signal to noise ratio, because we have found it to be one of the important parameters for several applications, which we'll show a bit later. So what we tried to prove this, or well, what we worked on proving.
Exactly.
But before that, I think just to jump also on the size and performance trade-off, again, I think this is a very good aspect to briefly cover. Basically, why are trade-offs necessary, and why is optimizing each part necessary, but also understanding the contributors to noise is necessary to know where you can optimize and where you cannot optimize. So to the overall noise level, the MEMS, the ASIC, and the package contribute, but they contribute in different extent, right, Somu?
Exactly. So if you just look at the graph, what you're seeing is it's a linear scale, which is is a bit interesting to see because usually we see all the plots when in a logarithmic scale, in dB scales, right? What you're looking at is over the frequency between 20 hertz to 20 kilohertz, how your noise levels look like, or your noise contribution is from a MEMS, from an ASIC, and also from the package in totality. So that includes every aspect of the package. And if you look at the curves, so the green is the MEMS, orange is the ASIC, and the gray would be the package. And if you just look at the left column close to the lower frequencies around 20 hertz, you see that the package contributes heavily in this case. So for a given case, whereas if you keep going forward along the frequency line, slowly you would see that the contribution from MEMS is higher. So that basically suggests that even if you have a bigger package over there, but you use the same MEMS in those higher frequencies, the MEMS would still continue to dominate. So you take the same MEMS, same ASIC, put it in instead of a 3.25 times 1.9 package, put it in a way bigger package, you wouldn't get a lot of a benefit, because the MEMS is the one which is dominating the noise. And that's where this whole play of MEMS, ASIC, and the package comes into the picture. And that's where we see our strengths lie, where we could focus on, hey, how can we deliver the best possible performance? What for this application, we have XYZ performance requirements. Okay, what are the package requirements? Okay, and then we see, okay, what are the MEMS and ASIC combination should be to address this? And in cumulative terms, you see that the total MEMS microphone noise, so the blue curve, is always a logarithmic sum of all the three noises over the frequency that we see, and that basically defines the SNR.
Okay, interesting. So the package noise contribution, this is predominantly a mechanical resonance type contribution, is that?
Yes,
right?
And also the thermal noise that's being generated. As well, there is a sound port that also is a contributing factor to it. So in totality, there are a few other components, and at Infineon, we try to model all of these noises, test them, verify them to have we could create we have a simulation platform where we could build on what the performance could be with package X, MEMS Y, and ASIC Z. what we could achieve.
Okay.
But I mean, there's limits to what
Yes.
you can do. So the let's say the 2.75 by 1.85 ATDP SNR is gonna be difficult.
Yeah.
Just from the sheer you need a certain back volume to achieve that. But of course, working on optimizing everything here. And
Yeah, I think we all have this conversation with people. What do you want me to do?
Exactly.
Break the laws of physics here.
Exactly. Yes.
If I could do that, I'd be a fairly rich guy by now. Probably.
Totally.
But I mean, also sometimes, I mean, if you look at and as was discussed, as we already hinted at with the voice user interfaces, right? First, we also have to look at why do we even need to optimize the microphone performance. I mean, people could say it picks up sound somehow, you know, it's good enough, which is a fair question. I mean, of course,
Okay.
and there are applications where you freely admit you don't need a good microphone, right? But there are applications where performance matters, and we want to just share a few glimpses of that, where we did some research kind of focused really on audio applications themselves. And the first one here being, as we already said, a bit the smart home devices or voice user interfaces, where Somu together with our engineers has planned and carried out research on answering the question, does the microphone SNR matter here? And the hypothesis for this whole experiment was based in what's called the inverse square law, meaning that the sound pressure level goes down if you increase the distance, right? I think so that sums it up quite in product marketing terms.
Yeah, in very simple terms now. So as sound waves, that's basically compressions and expansion that's happened as it translates over the air as a medium. And there are a lot of different losses that could happen: reflections, dissipation, and so on and so forth. And basically, in an anechoic condition, so to say, with doubling the distance, you lose 6 dB every time. But however, in reality, it's a bit different, because you also add reverberation and things like that, which might even help to recover some of those losses. And there, basically, I think Colin, you alluded to this as well. So the far field voice pickup, how would that look like? And that was something that we wanted to see. What could be a use case? Yes, far field voice pickup, and then how to explain this or translate this to our customers. If you look at the standard certifications for this voice user interface devices, so you see right at the center in purple, this is where the standards lie. They focus on testing at standard voice level at a certain specific distance, which is not that, which cannot be categorized as far field or anything. And they tested, okay, this works, fine, certified. But there are natural use cases, or what happens in reality is, for example, you are in another room. Let's say you have an open kitchen and your smart home device is in the living room, and you want to give a quick command to it, and then you keep on saying, hey Alexa or Siri or anything. You keep on saying it so many times before it listens to it. As Julian said, so some companies are okay, or some OEMs might be okay with this, but from a customer experience perspective, this is something that falls into the corner use cases, where customer knows it's a device. Okay, it works when I'm looking at it, when I'm super close to it, it works fine. But but other use cases it doesn't. The other use cases, for example, soft whisper. Example, you are a lot of the people use voice assistant devices more like an alarm clock, and they have it next to their bed. So imagine a situation where you're lying in the bed with next to your partner. Your partner is already asleep. She's tired from the day's work, and you want to quickly set up the alarm. And in this case, you wouldn't like to say it out loud right? You would like to just whisper it and you want this device to pick it up. Yeah. But somehow a lot of the times it doesn't work. And then you have to manually enter it in your phone. Okay, this is my alarm. Now.
Or it's even worse. It doesn't understand you correctly and it sets the alarm too early.
Yeah. And to avoid these kind of false detections or false positives, we try to look into, hey, what could be these use cases, one, and can we test them? 2, and 3, what is the right way to test it? And 4, if there is any value of going with a higher SNR microphone. And that's basically what we did at component level, as we would see in the next slides.
Yeah,
I actually worked on a far field product where the microphone array was under the bed, and you had to be able to lie in the bed and get it to hear you.
Wow.
It took a long time to get it to work.
I can totally imagine. And then on top of that, how was it discussing with the customer on the use of microphones?
Yeah, I mean, a lot of that was about obviously the SNR and all that was very important, but the biggest problem there was multipath reflection. This thing's literally under the bed, and everything's bouncing off the floor. And anyway, sorry, I tell you.
No worries.
No. It's always fun to listen to the experiences in this field, because they match so well with a lot of the conversations that we have as well, trying to explain things. But so coming back, so what we looked into is normal voice. So if you're just having a normal conversation with your Alexa or Siri device, let's say, and you just use it normal voice, standard use case, and you just change the microphones. You go with the standard 65 and you compare it with a higher SNR microphones, like 70-ish dB from Infineon. What we looked into is we see a 5% higher hit rate. So the speech intelligibility improves by 5%. You would say, okay, that's not much. 5% in reality might be a bit might not be that clearly visible. But then you move to the next use case, that is you're in your kitchen, you're passing on a command, you have an open door or an open kitchen setup, and your device is sitting in the living room at, let's say, around 5 meters distance or so from where you are. And you are not facing the device, but you're still giving the commands. Like switch on the lights or play my favorite song, as you see it here as an example. There is a 25% improvement. I think at that point you start wondering, okay, maybe there is something here where you could improve it as well. And then we look into another use case, that's the whisper speech. So you have it next to your bed, let's say, and you want to set the alarm, the exact use case that we discussed. And you see with the higher SNR microphone, because you're in a bedroom kind of an environment where the noise levels are even lower, you are able to achieve a 40% higher hit rate. And that's where we see, okay, already just by changing the microphone and the same setup, just tuned to enable use of a better microphone, you can already achieve between 25 to 40% improvement to address the other use cases that we are looking into. So I think the next slide focuses a bit more on what we tested and how we tested it. We actually have an app note which goes into way more detail on what we did. So on the left, you see the soft voice scenario where we compared a 65 dB SNR microphone with the Infineon high SNR microphone. And on the y-axis, you see the ABC MRT score. So ABC MRT is just one way, a modified rhyme testing method, where it looks into how well your microphone can distinguish between similar sounding words. Let's say you say bat, tat, rat, sat, dat, for example, and how well can it distinguish between them. And this is super crucial in this whispering scenarios, because you are somewhere close to mumbling your words, and there how well it could distinguish between what you just mumbled. And that's where you start seeing the difference between using a standard microphone or going for a higher SNR microphone.
Okay.
Similar case. Yes.
Is that application note available to the public?
Yes, it's available on the Infineon website.
So we can put the link in the notes below, so everybody watching check it out.
Yes,
Yes.
perfect. Yes, and the second use case as is the far field performance. So kitchen to living room kind of an environment. You see that for lower noise levels, unless you have super high background noises, like a construction, your living room is next to a construction site, you are able to improve the performance even further. So you still from a standard use case, so you get up to a 25% better far field response using a higher SNR mic.
Okay.
Okay, good.
So that's basically one of the applications where we looked into at a component level how we could improve the user experience, how we could address some key use cases, and how the users can benefit from using a higher SNR microphones in the voice assistant or the virtual assistant devices, as we call it.
All right.
Yeah, and I think, I mean, voice assistant devices, that's a crucial part. So what I always use as a, yeah, to remember what this test was about is how good is the input then for the algorithm, right? Because Alexa, Siri, I mean, they take the microphone input and then they, you know, translate it to yeah, how it, yeah, to into its components, what it's supposed to mean, what is the command, but
Right.
that doesn't tell you yet about, you know, how well it, well, arguably how well it sounded, right? Because what sounds good to an algorithm doesn't necessarily mean that it sounds good to a computer. Or put it a bit differently, if you're standing, yeah, in the wind or somewhere and you're on the phone, it might be heavily distorted, but you might still hear what the other person is trying to say. It might just not be very enjoyable. So
Mhm.
the one aspect that was tested with this ABC MRT score is the algorithm input, but the other crucial use case, of course, is communication, and how good does it sound to a human. And
Mhm.
there, this ABC MRT test, Somu, is it fair to say, is not the most ideal one? Am I going too far,
Totally.
or is this okay?
No, I
Yeah,
would say so. Yes.
so
Yes.
we were looking for a way to, yeah, for different tests, and to look here on the speech quality. And there, there's another test or another standard, right? The Polka test, the perceptual objective listening quality analysis test. What this in essence does is, I mean, similar to the AVC MRT, it gives a mean opinion score, a score to how good a recording sounds.
Yes.
And a very basic test that we've done here back in the day was just what is the, on a component level, the rating of speech in this PolkaMOS test. And there, I mean, for audio engineers, won't be a surprise, right, that high SNR mic has a higher rating here. I mean, I guess you're not surprised by that.
Oh,
But yeah,
Yeah.
to be quite frank, I mean, with the response that we get just for showing this, and it's makes total sense, is okay. This is if I just look at the component level, but what about if I put this somewhere? You know,
Exactly.
oftentimes it's about yeah, but the algorithms will do all the work, or it's going to be built in the device and stuff like that, right? Which I mean, yeah, this is a lab setting here, and we have to look at how would this be then on a system level. And
right.
this, I think,
Yeah.
Somu, where the challenge that you took up, yeah,
To
to
basically,
answer this question, how can we rate and test the quality in communication devices?
exactly. So just a quick recap. So ABC MRT focuses on speech intelligibility for a machine, and
Mm.
PolkaMOS, as you know very well, it focuses more on the quality. So by quality, you mean how is this tested? So you have pre-recorded files that is being played over a speaker. The system has a record of this file, the energy spectrum or the frequency spectrum of this original file. You capture it with a microphone and you try to do a one-on-one comparison of this. So the closer it matches, the higher is your Polka score, with a maximum score of 4.5 that you can achieve, which says, okay, this is perfect match, or it's the best possible match that you can have. And the lowest match, so if it doesn't match that well, the lowest that you can get is a 1. So standard, I would say, for laptops and conference devices, you should get at least a 3.5 to have a decent level of understanding to be achieved. but that would be again falling into the standard use cases or standard focus. But we want to enable to make sure that you could basically take your devices, take your laptops, go to a meeting room, and you wouldn't need additional accessories, for example, to enable this audio use cases.
Yeah.
As you can see.
Yes.
Yes. So wouldn't it be amazing? So having a laptop that could basically can do everything that you need in a communication perspective for conferencing, rather than putting on headsets all the time. And that's the, as Julian said, so that's basically the challenge that we wanted to address, because this was also a question coming through our discussions with a lot of OEMs, that okay, but tell us how would this look like in a system. And then we jumped into basically to understand how the system looks like. That's basically the next slide. So what you see here, super complex, but let's make it easy. Let's start from the extreme left. You have two digital microphones. That's generally how it looks like as an audio interface. When it comes to a laptop, you have it right in front of you next to your camera. So on the same camera module, two microphones with sound ports facing towards you. And then these signals are being picked up, digital microphones picked up and send it to a codec, which lies mostly in your keypad. So underneath your keypad with the entire motherboard system, which has a codec for controls, for gain controls and things like that. And then this signal is being set to the next part, which is the audio preprocessor block, which, let's say you're using a conferencing tool or a conferencing app like Microsoft Teams, or be it a WebEx
Zoom,
or a Zoom,
right
what we are on, and it adds to some other additional signal processing options. And this is then sent to an encoder to transfer the signals over VoIP over the internet and fed back to the user. So in this case, while I'm speaking, not with this time with the headsets, but still it's the same case. So this microphone picks it up, sends it to the codec of my laptop, does gain controls. The Zoom in this case adds some pre-processing if
Right.
could be enabled or disabled, sent over the internet, and then you hear it on the other side. And we wanted to understand basically if we enable and disable certain blocks in this architecture, can we see the impact of changing the microphones? Is there an impact?
Right.
And that's what we try to dive deeper into to understand what's the effect of the microphone performance.
Okay.
So here you see three cases. Starting from the left again, you have a standard laptop with standard microphones. You have Microsoft Teams or a Zoom-like application with and without the signal processing. So you could enable and disable this. Second is we use Infineon microphones. Now you would see how we interfaced it with the signal processing and Infineon microphones. So 69 dB SNR and a 72 dB SNR without signal processing. So the three use cases that we try to tackle. Let's go to the next slide.
Yep.
So as you know, so microphone positioning, in this case, right on the top bezel where the two microphones are located.
Right.
And yes, so this is our testing environment. So the block basically, so the gray block basically shows that this is our anechoic room where we are doing the test. On the left, you have an artificial mouth, which would utter the words or the speech. Then you have the laptop inside this box, placed at a certain angle based on the certification guidelines that some of these communication or conferencing platforms provide. And this has a reference PC for doing the comparison. So the Polka comparison, similar like Polka comparisons. So on the left bottom, you see our actual setup with the same arrangement placed at a distance of 1 meter, and then also increased further depending on what we are testing. And on the right bottom, you see that's the interesting part, is how we interfaced our microphones. So in the first case, we had the laptop mics. In case 2 and 3, we have an Audio Hub analog board that we have built up. So the information to that also we could share. You could have it in the link below. And This board is able to stream 24-bit high quality data over USB to your laptop. And that's basically, we are bypassing the microphones that's there on the laptop using this USB interface to send the entire signal. And that's basically what you have over here. We changed the microphones because these are on flexes. The best part for us was that the positioning or the spacing between them is just perfect. It just meets it perfectly. So also if there is some signal processing happening or some beam forming happening over there, that could also be addressed over there. Especially, we would like to thank VoiceX. It's our testing lab partner in China, because for the system testing environment is something where we are growing our expertise. And that's where, as Julian mentioned, not only in terms of packaging, we partner up with the likes of Gore-Tex or Mary. We also partner up with system players or system testing players, in this case, VoiceX in Shenzhen, China. They are our testing partner. We work together with them to build up this use case testing environment, and that's where we did all our tests. They are quite proficient in these kind of laptop testings, and we work closely with them also to learn together with them. And what did we test? So let's look at the three cases. As always, we look into cases. What are the use cases that we have? Case one stands for closed scenario. Basically, you have your laptop, you're sitting in front of your laptop and just using the mics. How would the performance look like? Second, you are in the proximity of your laptop, but you have the freedom to move around your laptop, or moving further away from the laptop. Can it still be able to pick up your audio properly? Or it just gets totally distorted. Third is the conference scenario, basically a far field conferencing application where you take the laptop, walk into a meeting room, and that's your conferencing device. You don't need an additional conferencing device. What would that look like? Yeah, there are still other areas that needs to be addressed on positioning of the microphones for a conferencing like applications. Maybe you need a third microphone to get more like a 360 audio pickup, but just from the distance
generally,
perspective,
right? I mean, it's about the general.
Yeah.
In which direction is it going, right?
Exactly.
Is it all signal processing, or does the mic have an impact? I think that's. I mean, this is at the beginning, I would say. I mean, the first tests that we've done.
Exactly. So yeah, so basically these are the three different use cases that we wanted to focus on, and we try to do the Polka-MOS score calculations through the entire audio ecosystem that we have. And let's have a look at the results. So this is with the audio processing block enabled. So you have the entire audio architecture, everything enabled. You are just switching from the laptop mics, which is in orange, to a 65, a 69, and a 72 dB SNR microphones.
Okay.
Here you see already in the lower ranges. So if you look at the x-axis, so that's the distance scale, already within the 1 to 2 meter range, you see a huge improvement that you can achieve of roughly 0.5 to 0.6 in MOS scores. And that's around 20% improvement that you could achieve already in this close to proximity scenario, just by improving the microphone. You're not improving anything, not trying to tune the system or anything, because to be very frank, we don't have the ability to tune the system yet. We don't have the access points basically to tune the system. And if you move further away, if you're trying to target this use cases like conferencing and far field conferencing and things, you could achieve an even further improvement of around 35%. Imagine the possibilities if you are able to also tune the system further, because the ADCs, the codecs are also tuned to a certain dynamic range for the current microphones. However, if you enable this, if you unlock this, you could achieve even better performances even at far field. So what we started as a theory seems like in reality, if it's implemented properly, could also enable a better high quality audio capturing for voice communication in laptop as well.
Okay, so could I ask you, I mean, just a thought occurring to me is, how much influence do you think, so in your scenario here, when you're testing with your microphones, they're outside the case of the laptop. So how much influence do you think the mechanical mounting of the mic has, and the aperture in the mechanicals to the microphone. So I can see a great improvement. Do you think it would be, you'd lose some of that if you were actually mounted inside the system?
That's an excellent question. And it's a very simple answer when it comes to laptops, actually.
Okay.
Because laptop in smartphones, it's way more complicated because you have an acoustic channel, which leads to, you have acoustic channel, you have a mesh or a membrane for other robustness protection for dust and particle, where you lead to a loss that we have seen in some of the devices of around 3 to 4 dB in performance.
Okay.
Whereas in laptops, it's way more easier because they don't use any acoustic channels. It's built on a camera module.
Right.
So you have the camera module and you just have the microphones built on top of it. And all that is covered is the plastic or the poly coating that you have around your laptop framework. So around your screen, and that's it.
Okay.
There is no acoustic channel there. And if it's glued properly, so you don't leave any air gaps, so you create some resonances in between. I think this would be way more easier to achieve with very lower losses when it comes to laptops.
Okay, thanks. Thanks for the answer.
Yes. Yeah, so that's also a very important area where we look into how we could not in laptops, but in other cases like smartphones, how we could further improve the audio performance and not lead to additional losses. So we also look very intensively into acoustic channel designing and how we could help our customers in that regard. Together with our electrical as well as mechanical models, we deep dive into this aspect as well.
Okay.
Yeah, it's usually a classic thing where I'm sure mobile phones and computers, people come to you to help solve the problems, and they're collaborative.
Yes.
One thing that can happen in less sophisticated companies, and it's, it wouldn't start to include people doing smart speakers, is they come to you with their mechanical design already finished and paid for,
yes.
and they're like, oh, we can't change anything. Or and in automotive, it could be similar.
Don't worry about it.
It's design driven, and oh, sorry, the design's got to be like this, or I don't know, Tim Cook's gonna cut our head off, something like this, So it's a challenge. It makes my life more difficult for all of us.
Totally happens all the time, and that's why we try to proactively share with our customers quite early on in the discussions. Hey, we also have this. In case you need any help, we have seen certain experiences with some reference designs. We say, the loss could be this much. Maybe if we work together already at the beginning stage, we could avoid all of this. We try our best. But yeah, you are absolutely right on that. Sometimes we get the designs as well. We see it. Okay, this was already done. We cannot change it. And the losses are 3-4 dBs. And it's like, I wish we could do something about it, but yes, no, totally.
It's very frustrating. It happens a lot, and not just with microphones.
Yes.
The most common one for me when doing smart connected devices is you get an ID design, and the customer has is made a large lump of metal, and they say the antenna's behind the metal. It's like, oh, okay, just go from here.
Yes, no, totally. And audio is that one delicate. I would call it a beast, or it's so sneaky or so easy just to lose the performance. You just make few tiny mistakes here and there in your signal chain, be it electrical or mechanical, you lose it. There is no value added to it. It's just that the entire system has to be robust, has to be tuned, or has to be designed in a way to achieve the best acoustic performance. And we totally understand that only by changing microphones we are not able to achieve that. And that's why we like to work together with the industry players to basically enable this whole signal chain, be it in electrical or the mechanical side of things, to make sure that the audio performance looks good, or what is intended to be the target.
Okay.
Thank you.
Yeah, and I think with that, let's have a quick look into the future. I mean, where are we going with this? I mean, we say we want to prove the value of high SNR, and I think we are seeing that the standards are changing also. I mean, as we said right before, 62, 65 dB SNR were a standard, but we are seeing that this higher performance is also being valued. I mean, if you look at this smartphone, the Snapdragon Insiders smartphone designed by Asus, where we're looking at the DxOMark, the French scoring company. Usually for cameras, they're quite well known, but also they do audio rating. And there they have said, I mean, they measured that the microphones have a dynamic range of 114 dB, and given it an extremely high rating on the recording. So the microphones and audio starts to matter. And where we are going is, as we said in the beginning, get smaller, higher performance. How can we, bring these two together? And this is where we're going in the future. And today, at least with our Infineon MEMS, we are at 73 dB SNR. We try to shrink this while keeping high performance. But the goal, or our goal, is to be on par with studio level capsule microphones. And our prototypes are slowly reaching this level of performance. So we are scratching here the 80 dB mark, so to say, and which is very exciting. And if we show just from a meeting we've had recently where people were like, they did not know that this was achievable in MEMS and this form factor, and we were like, we also did not know. And we came up with this. So to come full circle, so to say, we are at the brink of reaching the studio level performance, 70 dB plus. Of course, as we said, right, not everyone needs this high performance, but we also like to find out, and as we've shown, is it always the case that you don't need it, or we just don't know about it yet, right? What's the real impact of performance on other things? So we keep continuing on this. What, for example, what we did not touch on today was hearables, for example, another whole booming field. But I think for us, the direction is clear that we want to improve the performance and have interesting conversations about it. So that's
Exactly
where we're going.
Yeah, we basically, so in one statement, we basically want to bring the audio recording studio in your pockets, in your ears, so you could pick up everything, you could do everything when it comes to audio, together with the system partners, of course, with your consumer devices. So everything should be possible.
Okay.
That's our mission.
Very interesting.
It's very impressive stuff.
Yep.
Any closing notes that we have here?
Well, I mean, it's very impressive. I learned a lot about MEMS today. So.
Yeah, absolutely. Do you guys have your contact details? How, if people have questions besides putting below, so we can put the Infineon, we'll put the whatever you guys got, Twitter, Instagram, all that good stuff that
Cool.
That tracks your life. And there's probably a whole webinar episode on how the microphones are listening to us constantly. We can talk about that another time.
Yep.
But yeah, Colin, did you have any final questions?
I think not. I think we've covered most of the things I was thinking of as we went through. So I appreciate it. I appreciate the answers. Very good.
All
Same
right.
here,
So
same
yeah, everybody watching, please like, subscribe, hit your comments up. We'll have some links in the comments below for some of the things we mentioned, like the application notes previously. And once again, Somu and Julian, thank you so much for joining us today. We really appreciate your time. It was fantastic.
Yeah,
Thanks to you guys.
Likewise. I have to say it's really great to have conversations about audio and to see that it's becoming more and more interesting and exciting, or also in our community, but also now going into other fields. So this is great stuff, and really thank you for giving us the opportunity to be on this podcast. Keep up the great work, because these are interesting conversations, really.
Okay. All right.
Perfect.
Well, thanks, guys.
It's been a pleasure. Thanks a lot. Thanks a lot.
Okay. See everybody next time.
All right.
Thank you.
Take care.
Take
Bye.
care. Bye-bye.
Right.